begin our discussion of regression, a very powerful procedure that moves us into the realm of modeling. Modeling is the idea of building an abstract representation of the real world that we can use for various purposes like simulation or prediction. Regression is a very powerful and generalizable procedure for studying relationships between and among variables. As recalled here, situation 2a represents the most basic form of regression, simple linear regression. As indicated, this is the two-variable scenario where we have a single response variable and a single predictor. For simple linear regression, both of these variables are interval-level variables. However, in discussing regression, we also will want to look at the more general situation where we have multiple predictors. Alongside situation 2a, we will discuss situation 2b of multiple regression. Multiple regression describes the more general modeling situation where we have multiple predictors. We can use multiple regression when we have an interval-level response variable and one or more predictor variables, at least one of which is also an interval-level variable. We may also have one or more nominal predictors, but for multiple regression, at least one of the predictors is interval level. If we have all nominal predictors, then we would use a form of the analysis of variance, a two-way or three-way ANOVA, etc. But if we have an interval-level response variable and multiple predictors, at least one of which is interval, then a multiple regression analysis is considered. In the initial upcoming modules, we will focus on the simple linear regression situation because it's easier to visualize what's happening for the single predictor scenario. We can graph the model in 2 dimensions to get a picture of the methodology and how it operates. But we keep the multiple regression situation in mind and recognize that everything we see for the single predictor situation extends to the multiple predictor situation. As we proceed, we will address some of the special considerations that arise when multiple predictors are available. This slide shows an example suitable for simple linear regression. We have 2 variables, both of which are interval-level variables. The response variable is the amount spent by a family at our store, and the predictor variable is family income. We are interested in whether there is evidence of a relationship between these variables, leading us to ask, what would it mean for there to be a relationship between the 2 variables? From the answer, we will identify a test statistic that is sensitive to whether or not there is such a relationship, and proceed from there. We begin with the most common form of a relationship as captured by a simple linear regression. We posit a linear relationship between the 2 interval-level variables in the real-world process. For instance, we might expect a linear relationship like the one shown here for our example, between the response variable of amount spent, denoted by y, and our predictor variable of income, denoted by x. The box presents the linear equation between these 2 variables for the line drawn in the figure. The equation is familiar to us from linear algebra. Here we denote the constants in the model using beta naught and beta 1. The linear model is beta naught plus beta 1 x. This is a proposal for the form of the relationship between these variables in the real-world process, a relationship that is unknown, but of interest. Beta naught and beta 1 are parameters. In the model, beta naught represents the y-intercept of the equation. The constant is what the value of y is when x equals 0. Graphically, it is the point at which the line crosses the y-axis, where x equals 0. The constant beta 1 represents the slope of the equation. The slope of the line is a measure of the degree to which y changes for each unit increase in x. As income goes up by 1 unit of income, the amount spent goes up by beta 1 units of amount spent. As drawn in this example, beta 1 is greater than 0, indicating a positive slope, meaning that as x increases, y increases. A negative value of beta 1 implies a negative relationship and a declining line, such that as x increases, y decreases. In contrast, on this slide, we see what no relationship would look like. For any income level, 2, 3, 4, 5, or whatever, the amount spent is the same. Knowing the income tells us nothing about the amount spent. For a linear model, as pictured, this corresponds to a line with beta 1 equals 0. Such a model just looks like y equals beta naught, where the value of y does not depend upon x whatsoever. There's no relationship between x and y. In fact, for this model, the line would be at y equals mu of y, as indicated. The process mean mu of y being the central tendency of the y values. So for a linear model, no relationship means that beta 1 equals 0. A linear relationship means that beta 1 does not equal 0 and can be either positive or negative. As mentioned, although our initial focus is on simple linear regression, we are mindful that our more general interest is in multiple regression. An expanded multiple regression example is shown. The amount spent at our store is still our interval level response variable, but now we have multiple predictor variables. At least one of the predictors is interval level, for example, income in this example. Though others of the predictors can be nominal level variables, for example, whether the shopper saw the ad or not. With multiple predictors, we have now multiple relationships of interest among these variables. We'll take a look at how we deal with there being multiple relationships when we expand our attention to multiple regression. As an outline, we formulate multiple regression as a series of steps. In this module, we discuss the first step, shown here. Step 1 is a statement about the unknown process. The first step is to specify the form of the model that we are proposing to describe the relationships we believe exist in the process. What predictor variables are reasonable? And what is the form of the relationship that we think each predictor has with the response variable? For example, a linear relationship or some other kind of relationship that we specify. For this step, we view the general formulation, shown here for the multiple regression situation with multiple predictors. This first step of specifying the model is something we do as an analyst. It's up to us to identify what variables we think might be related to our response variable in the real-world process, and include those in the model. And although it's not apparent from the model form as shown here, recognize that we can specify many different kinds of relationship within this form. The regression procedure is very general, which is one of the reasons it's so widely used. The predictors xi in this model can be individual variables like income or time of day. The xi can be a combination of two or more variables within a single xi term, like income squared or income times time of day. Or the xi can be of any functional form of one or more variables. For example, the log of the income or the arcsine of the income. Although linear single predictor terms in a model are by far the most common, other types of xi terms are used to capture different kinds of relationship that might exist between the predictor variables and the response variable. The major point in step 1 of specifying the model is, though, that we need to imagine what the relevant relationships might be. The specification of the model comes from us, not from the data or from the statistical analysis. One of the major tasks for the analyst is this step 1, specifying the model. Okay, our model has this general form in which we identify the terms in the model x1 through xk using one or more predictors available to us and judged to be potentially relevant. let's look at the components of the multiple regression model. The beta I in the model, beta naught, beta 1, beta 2 through beta k, are constants in the model. These beta I describe the relationship between our response variable and the predictors in the real-world process. The beta I are unknown parameters, characteristics of the process that are fixed, of interest but unknown. In the multiple regression with k greater than 1 values of xi, the value of beta naught is the equivalent of the y-intercept in simple regression, but now extended to k plus 1 multidimensional space. Beta naught corresponds to the value of y when all of the xi equals 0 in the model. If all the xi equals 0, then y equals beta naught. As described earlier, in this case y equals mu of y, the mean of y without considering the predictors. This is appropriate since in this case none of the predictors has a relationship with y. The coefficients beta 1 through beta k are equivalents to the slope. Generally, they describe the degree to which y changes for each 1 unit increase in that value of xi. We will come back to discuss these later for the multiple regression case to be more precise. The component of the model that we want to highlight now, though, is the last term in the model. The epsilon term is called an error term, and it is probabilistic in nature. The beta I are fixed constants, fixed parameters of the process. The error term epsilon is a random variable associated with the process. It is described by a probability distribution and is a critical component of the model. It plays a central role in subsequent regression steps that we will discuss later. With this epsilon in the model, we recognize that our model is a probabilistic model. In this way, the regression model is not like the deterministic models that you might see in certain sciences like physics. In physics, you might have a formula like force equals mass times acceleration. Given a particular mass and a given acceleration, the formula gives you a specific value of the associated force. And there's no uncertainty expressed about that value. In the regression model, that's not the case. The variability of any process is explicitly recognized and incorporated into the model with this epsilon term in the model. The epsilon term is a random, probabilistic component of the model. The model says, you give me an x1 through xk, and I'll give you a value of y approximately within some variable epsilon. The y value provided by the model is uncertain, even if we know all the xi and all the beta I. This uncertainty is formally captured within the model through the epsilon term, this random component. That's an important thing to recognize about the regression model, and why specifying this epsilon as part of the hypothesized model is essential. The real-world variability and the uncertainty that arises from it are explicitly recognized and incorporated into the model as part of the model itself. As mentioned, we'll see more of the role that epsilon plays in regression as we proceed through the following steps in the regression procedure. After specifying the model, we next will use our sample information to fit the model to the data. In the previous module, we specified the form of the regression model as step 1 of the procedure. In step 2, we fit the model to the data. We identify what the relationships that we specified look like in our sample data. Doing this will provide us with the appropriate statistics that we will need to perform the inference we want to do about the relationships in the process. Let's start with the general form and notation used in step 2, relative to what we did in step 1. Here we have the general form of the hypothesized model we specified in the step 1. We identify the terms in the model x1 through xk using one or more predictors available to us and judged to be potentially relevant. The beta I in the model, beta 0, beta 1, beta 2 through beta k, are constants that describe the relationship between our response variable and these predictors in the real-world process. The beta I are unknown parameters, characteristics of the process that are fixed, of interest, but unknown. The error term epsilon is a random variable associated with the process. It is described by a probability distribution and formally incorporates the uncertainty we still have about the response variable, even knowing the predictors. We explicitly acknowledge that the predictors aren't perfect. They do not give us a value of y for certain. This model is a model of the process. It describes what we are proposing for the relationships in the real world, in the process. The beta I describe the relationships between y and the set of xi in the process within the form of the model we specified in step 1. The parameters associated with the process are unknown, but they are where our interest lies, in understanding what's happening in the real world. Now, we get some sample information. We use the sample information to determine how the model is operating in the sample. Fitting the model is the step of using our sample to determine what the relationship is between y and the set of xi in the sample, as specified by the hypothesized model. As shown in the slide, the format for the corresponding fitted model is beta hat naught plus beta hat 1 times x1 plus beta hat 2 times x2 plus up to beta hat k times xk. As we see, fitting the model involves coming up with values of beta hat I that describe the relationships in the sample. In this notation, we use the hats to indicate these values are statistics, known values calculated from the data. Using these statistics, along with any given set of xi values, we can calculate an estimated value for our response variable, y. As indicated on the slide, we call this y hat given the set of xi, or just y hat for short. Again, the hat indicates that this value is calculated from sample information. Furthermore, each individual in our sample has a set of x values in our data. We can use these to find an estimated value of y called y hat for each individual in our sample. There is no epsilon for the fitted model. The fitted model is known sample information. There's no uncertainty associated with the fitted model. We know our data, and we know the relationships in the data. That's step 2. Step 2 involves coming up with these beta hat I from I equals 0 through k that best describe the relationship between the observed values of y and the set of xi in the sample and serve as our best estimates of the process parameters beta I that describe the relationship between y and the set of xi being produced by the process. The model y hat equals beta hat naught plus beta hat 1 times x1 plus beta hat 2 times x2 plus through beta hat k times xk is our best fit model based on the sample information. But how do we identify this best fit model and the beta hat I that describe this fitted model? As noted in a previous module, we can apply the step of fitting the model generally to the multiple regression situation 2b. However, for example purposes, we will use the simple linear regression situation 2a to visualize the procedure used to fit our model. For the single predictor scenario, we can graph the model in 2 dimensions to get a picture of the methodology and how it operates. But recognize that everything we see for the single predictor situation extends to the multiple predictor situation. Keep this in mind. In subsequent modules, we will address some of the special considerations that arise when multiple predictors are available. Consider a set of sample data points like those in this graph. We have an interval level response variable y and a single interval level predictor variable x, and we have sample observations shown by the scatter plot. We want the best line that goes through these points and that captures any linear relationship in the data between y and x. How do we go about determining a best fit line? Now shown is a line of the type that we're trying to determine, a line that we propose as a possibility for capturing the relationship between y and x in the sample data. We know this involves determining values of beta hat naught and beta hat 1, forming the line y hat equals beta hat naught plus beta hat 1 times x. For each individual I in our sample, using that individual's value of xi, we would use this line to find a predicted value of y, namely y hat I. Focus on one of the data points in the scatter plot, the point for individual I equals 2, shown in green. According to our hypothesized model for the process, this data point was generated by the equation highlighted in green. For individual I equals 2, this point has a y value, namely y2, that is hypothesized to be related to the x value x2 by the equation shown. For individual 2, y2 equals beta naught plus beta 1 x2 plus epsilon 2. Note that we appropriately use the parameters beta naught and beta 1 as well as the value epsilon 2 to describe the point x2, y2, which is generated from the process. Beta naught, beta 1, and epsilon 2 are all features of the process, and as such unknown. Y equals beta naught plus beta 1x plus epsilon is the process model. It is our hypothesized model for what is happening in the real world. And each of the other points in the scatter plot has a similar equation associated with it for I equals 1, 3, and 4. For these points, one thing we can imagine doing is to take the difference between the point y and the predicted value y hat for the line in red that we're considering as a possible best fit. The difference between y and y hat for individual I equals 2 is added to the picture in blue. This corresponds to the discrepancy between the proposed line's prediction, y hat, and the actual value y. Our proposed line, y hat equals beta hat naught plus beta hat 1 times x, describes the relationship between the y and x values in the sample, providing a predicted value of y hat, for each sample point. Y equals beta naught plus beta 1 times x plus epsilon is how we think the y is related to x in the process. What does this blue line, y minus y hat, represent? Y minus y hat is the beta parts of the process model plus epsilon, minus the beta hat parts of the sample model. Thus, y minus y hat can be thought of as representing our best estimate of the error term, epsilon, for that individual in the sample. As an estimate of epsilon, we can denote this as epsilon hat, as is done in the figure for the segment in blue for individual I equals 2. y2 minus y hat 2 equals epsilon hat 2. And we can do this for every other point, for I equals 1, 3, and 4 as well. The red line is the line we are imagining as a possible best fit line, as our best estimate of the process model that is highlighted in yellow. For each individual in our sample, relative to the red line, we have a value of epsilon hat. Let's use these to identify our best fit line. One thing that we can imagine doing is to say that a best fit line might be one such that if we add all the values of epsilon hat from our sample, a best fit line should make the sum of these epsilon hat as small as possible. Thus, one reasonable criterion for identifying a best fit line is a line that makes the sum of these differences, from the actual points to our estimates, as small as possible. This is a good criterion, but unfortunately it is not sufficient to identify a unique best fit line. This is because it is mathematically true that any red line that passes through the point x bar, y bar will satisfy this criterion. In fact, for any line that passes through the point x bar, y bar, the sum of the epsilon hat will be 0. This mathematical fact arises from the nature of the sample mean as a measure of central tendency. As we have seen, the mean is the value that balances distances above and below it. The same idea applies here. Any line through the sample means, that is, through the point x bar, y bar, will exactly balance the distances above and below, and will have a sum of the epsilon hat equals 0. Although choosing a line for which the sum of the epsilon hat is 0 is a good criterion, it is not sufficient. There are an infinite number of lines that can pass through the point x bar, y bar, and satisfy this criterion. The criterion does not give us a unique best fit line. A modification of this criteria that we might imagine is to minimize the sum of the absolute values of the distances epsilon hat. But there's actually a better criterion, one that provides better estimates of the beta I, as well as being more mathematically tractable. It is this criterion we will employ. The criterion we will use involves calculating the square of each of the epsilon hat values, as shown by the blue square boxes now in the figure. For each individual, we find the epsilon hat squared. Then we add them up and try to make the sum of the squares as small as possible. There is one and only one line that satisfies this criterion. Only one line minimizes the sum of these squared error terms, the epsilon hat. The line is called the least squares regression line. The criterion is to minimize the sum of squared error terms, denoted as the SS error. We calculate the epsilon hat for each observation in our sample. These are equal to y minus y hat and are called observed errors or residual terms. We square these terms and sum them for all of our sample data. We identify the unique line that minimizes this sum. We should also note that this unique line passes through the point x bar, y bar. The line that satisfies the least squares criterion also satisfies the criterion that we discussed on the previous slide. This then is the criterion we'll use to identify our best fit line, now written at the bottom in its general form. Mathematically, based on this criterion, we can derive formulas for the beta hat naught and beta hat 1 that correspond to this best fit line. We won't repeat those formulas in this module. They are readily available in textbooks if you're interested. We obtain the beta hat values from R, or other computer software. From this discussion, though, we understand what the beta hat values represent. They are the coefficients for this fitted line that describes the relationship between x and y in the sample data, and that provide an estimate of the relationship between x and y for the real-world process. The fitted line is defined as the unique line that satisfies the least squares criterion of minimizing the sum of squared errors between the data points and the line. While discussing the sum of squared errors, let's define one other important statistic. This statistic relates to the residuals, the epsilon hat values that are in blue in the figure and represent the difference y minus y hat for each individual in our sample. The statistic is the standard error of the residuals and represents the standard deviation of these epsilon hat values around the regression line. Being the standard deviation of the epsilon hat values, the standard error of the residuals has the notation S sub epsilon hat. It is the square root of the variance of the residuals. The variance is the sum of squared errors, SS error, divided by the degrees of freedom error. We call it the sum of squared errors is the sum of the epsilon hat square values. That is the sum of the squares of the differences, y minus y hat. To find the variance, the sum of squared errors is then divided by its degrees of freedom. In the simple linear regression case, the degrees of freedom are n minus 2. Note two things about the standard error. First, it is a standard deviation of the residuals, calculated in the usual way. To calculate a standard deviation, we take the difference of each value from its mean. We call it the sum of the epsilon hat is 0. This is a feature we noted in this module a short time ago. The mean of the epsilon hat is 0. This implies that the variance of the epsilon hat is the sum of the epsilon hat minus 0 squared divided by the degrees of freedom. We then take the square root to convert the variance to the standard deviation. That is the formula we have on the screen. The S sub epsilon hat, the standard error of the residuals, is the standard deviation of the points around the regression line, as captured by the epsilon hat equals y minus y hat. This standard error plays an important role in the inference step of regression that we'll see in a later module. Second, another point to make about this standard error concerns the degrees of freedom. Why are the degrees of freedom for the calculation of this variance of the residuals in the single linear regression case equal to n minus 2? The reason goes back to what the degrees of freedom represent, namely the number of independent pieces of information that enter the calculation. We start with n observations in our sample, but In order to calculate SS error, we need y hat first. As shown in red, finding y hat involves knowing beta hat naught and beta hat 1. Knowing these, we no longer have n independent pieces of information in our sample. We only have n minus 2. Consider this as taking 2 degrees of freedom to calculate the 2 beta hat, leaving n minus 2 degrees of freedom for calculating SS error. Thus, the degrees of freedom for this calculation is n minus 2. This completes step 2 of our outline. We specified our model describing what we think the relationships look like in the process. We collect some sample information. We use the sample information to fit the model, deriving statistics, the beta hat values that are our estimates of the parameters, the beta values. We're ready to proceed to the next steps. We turn to the assumptions that underlie the model fitting that we have seen and the inferences that we will see within regression analysis. Returning to our outline, we've discussed steps 1 and 2. In step 1, we specify the model, describing what we believe are the relationships between y and the predictors x. The model is a proposal about the process and how it's operating. In step 2, we fit the model using sample data. We identify the relationships between y and the predictors for our sample based on our specified model. We actually made some unstated assumptions in doing this model fitting. Eventually, we also will want to make inferences from what we're seeing in the sample to what we think is going on for the process that generated the sample. To do these procedures, we need to make some assumptions. In this module, we address the assumptions explicitly, including tools for checking the assumptions. The first 2 assumptions that we need are familiar to us: random sampling and stability over time. For randomness, we assume that there's no bias in how our sample is drawn or in how the measures are collected from the sample. For stability over time, we assume that the process and the relationships within that process are stable over the time period of interest. The additional group of assumptions that we need to make for regression are all assumptions about the epsilon random variable in our hypothesized model, repeated here. The hypothesized model specifies how we think the relationships are operating within the process, namely that y equals beta naught plus beta 1x1 plus through beta kxk plus epsilon. The epsilon is a random variable that can be described by a probability distribution like any random variable we have seen. For example, y is a random variable, as are each of the predictors. That can be described as coming from some probability distribution. The error term epsilon is an unexplained component of each y value from the process. Although unknown, as a feature of the process, we assume that these random components are regular. Specifically, we assume that the error terms epsilon are normally distributed with a mean of 0 and a common standard deviation sigma for any possible combination of values for the set of predictors, set of xi. We assume that all the epsilon come from the same normal distribution. This slide is a visual representation of the assumptions being made about the epsilon, shown for the simple linear regression case where we have a single predictor x. The straight line in the diagram is the linear portion of the hypothesized model, y equals beta naught plus beta 1x. According to the model, the y values can be described as related to the predictor x by the equation y equals beta naught plus beta 1x plus epsilon. Each y is described as the point on this line plus some random component, epsilon. The assumption is that For every value of x, the epsilon come from a normal distribution with mean 0. This means that every value of y comes from a normal distribution centered at the regression line and with standard deviation sigma. This is illustrated in the figure by a series of normal distributions that should be imagined as being vertical to the picture on the slide. For example, at the far left, the values of y in the process when x equals x1 can be described as coming from the normal distribution at left. The y values when x equals x1 have a mean equal beta naught plus beta 1 x1 and a standard deviation of sigma. For x equals x3 at the far right, the values of y in the process can be described as coming from the normal distribution at the right. The y values when x equals x3 have a mean equal beta naught plus beta 1 x3 and the same standard deviation of sigma. Assuming that epsilon is distributed normally with a mean of 0 and a standard deviation of sigma means that the y values are coming from a series of normal distributions. All the normal distributions have the same standard deviation, sigma. The y values come from a ridge of normal distributions centered around the regression line. For the process, we assume the y values are normally scattered around this line with a common standard deviation, and for every value of x. This is what the assumptions about epsilon look like for regression. At this point, let's explicitly recognize an important consequence of these assumptions about epsilon. In the general, multiple regression case, the hypothesized model is y equals beta naught plus beta 1 x1 plus through beta k xk plus epsilon. This equation captures relationships between y and the set of predictor variables xi. As the values of the predictor variables change, we expect y to change since they are hypothesized to be related. When we did not have the predictors, the process mean was some single value mu of y that we estimated using a sample mean y bar. Now, we hypothesize that the process mean of y will depend on the values of the predictors. We may ask then, if this is the equation for y, what is the process mean, mu of y, for a group of individuals who share a set of xi values? That is, what is the mu of y given a set of xi? Well, y equals the beta parts of the model plus epsilon. The mean of y equals the mean of each of the beta parts of the model plus the mean of epsilon. Okay, the mean of beta naught is beta naught, since beta naught is a fixed constant value. The mean of beta 1 x1 is beta 1 x1, since beta 1 is a fixed constant, and we are identifying the mean of y for a given set of xi, so x1 is fixed here as well. The same holds for all the remaining terms through beta k xk. The mean of beta k xk is beta k xk. Finally, we have the mean of epsilon. By assumption, the mean of epsilon is 0. Therefore, we see that one consequence of our assumptions is that the mean of y given a set of xi equals beta naught plus beta 1 x1 plus through beta k xk. Our proposed regression line can be thought of as an hypothesized line of means. Furthermore, we can now understand our model as proposing that an individual value of y can be represented as its mean for a given set of predictor values plus a random, normally distributed error component epsilon. That is, y equals the mean of y for a given set of xi plus epsilon. Returning to our graph, the regression line is recognized as a line of means. And more generally, for multiple regression, the hypothesized model without the error term epsilon is recognized as a hyperplane of means. It is a model of the mean of y for a given set of x values. For example, in this graph at x equals x2, the point on the line indicated by the large dot corresponds to the mean of y when x equals x2. Similarly, the model represents the mean of y for any specified values of the predictors xi. Individual values of y when x equals x2 correspond to this mean plus some error term drawn from the normal distribution indicated on the graph around the large dot. These then are the assumptions made for fitting and performing inference with the regression model. The assumptions apply to both the simple linear regression situation as well as the more general multiple regression situation. Apply our regression analysis, as usual, we want to check the assumptions that we make to the extent we are able. Returning to our outline, we started on step 3 by identifying the assumptions being made. We now want to complete step 3 by checking those assumptions. Let's demonstrate assumption checking using this real estate example. The situation is one in which the agency is constructing a predictive model for house sale prices entered in the database in thousands of dollars from a single predictor of house size, measured in hundreds of square feet. The first two assumptions are our usual ones of random sampling and stability over time. Also, as usual in our examples, we are not able to check these assumptions with the data we have. Still, we want to consider these assumptions within the decision setting and whether we can clearly identify a specific strong reason to believe that one or another of these does not hold. For random sampling, we don't have information about the sampling procedure. An unbiased sample should have been possible, and we have no evidence to say otherwise here. For stability, we would generally expect any relationship between house price and house size to be fairly stable over a reasonable period of time within a given geographic area. There's no clear evidence to doubt the assumption in this decision situation. Finally, we have a set of assumptions being made about the error term epsilon in our process model. We assume that the error terms epsilon are normally distributed with a mean of 0 and a common standard deviation sigma for any possible combination of values for the set of predictors xi. For our simple linear regression example, this is for any possible values of our single predictor of house size. We assume that all the epsilon come from the same normal distribution. Having these assumptions about the epsilon, we move to how we might check the assumptions, whether they hold or not. Unlike the first two assumptions, we can check the assumptions about the epsilon using our sample data. To do so, we will use the observed residuals that we calculate from our sample, namely the epsilon hat values. A y minus y hat value can be calculated for each individual I in the dataset. This subtraction involves the y equals beta terms plus epsilon in our hypothesized model, minus the y hat equals beta hat terms from our fitted model, leaving us with epsilon hat as an estimate of the epsilon. We have an epsilon hat for each individual in our sample, and the epsilon hat are estimates of the epsilon terms in the hypothesized model for each individual in our sample. Similarly to what we have done in the past, we can use the epsilon hat values as a check on the assumptions being made about the epsilon in our model. We are assuming that the epsilon values for our process are normally distributed with a mean 0 and a standard deviation sigma for any possible values of house size. If the epsilon values have this distribution, then the epsilon hats, being estimates of the epsilon values, should approximately have the same distribution. We expect the epsilon hat values calculated for each individual in our sample to not be too far from being normally distributed with a mean 0 and a common standard deviation sigma across all the house size values in our sample. We can use this expectation as a check of our assumptions concerning the epsilon. Let's consider procedures for doing this. As shown, we are looking to check the assumptions being made about the epsilon values that are features of the process, using the residual values, the epsilon hat, from the sample. To do so, we can break the set of assumptions about the epsilon values into two parts. The first part of the assumptions is that the epsilon in the process are normally distributed. We check this using the residuals calculated from the sample. As we have seen in an earlier module, checking this assumption is equivalent to performing the hypothesis test shown here. H0 is the assumption of normality. HA is that the residuals are not normally distributed. In blue is an example of the LM function used in R to perform the linear modeling of regression. As arguments of the function, we use the y variable, followed by a tilde, then the predictor. This is read as modeling price as a function of size. We save the result of this modeling in the data frame fit, that then contains a host of information about the modeling that we can access. For example, the residuals, epsilon hat, for each individual I in our sample are stored in fit $residuals. We can use these observations to test for normality. We've already seen procedures for checking the normality of a distribution in an earlier module. We graph the histogram of the epsilon hat at left. We construct a probability or QQ plot for the epsilon hat in the center, and we do a Shapiro-Wilk test for normality at right. We have seen these procedures before, and we apply them here to test the normality of the error terms. In this example, the histogram is somewhat flatter than we would expect, but not too spread out. Noted is that the standard deviation of the residuals, found using the SD function in R, is about 10. From the histogram, we see that most of the observations are within one standard deviation, and all are within two standard deviations of the mean of 0. This does not differ from what we would expect for a normal distribution. The probability plot shows some, though not major, deviations from the straight line. It is generally not bad. The Shapiro-Wilk test has a p-value equals 0.22, which is not particularly low. So altogether, there's not clear evidence that would lead us to reject H0. A violation of the normality assumption is not concluded. That completes the test of the normality component of the assumptions being made about the epsilon values. The other aspects of the assumptions are that the distribution of the epsilon has a mean of 0 and a standard deviation sigma that is the same across all of our possible predictor values. We check these parts of our assumptions using a residual plot. For the simple linear regression, a residual plot is a scatter plot that displays the residuals, epsilon hat, against the predictor values x. The epsilon hat should have a mean of 0 and a fixed standard deviation across all possible values of x. To check this, we plot the residuals as a function of the predictor values to see if the distribution across the predictors clearly deviates from this expectation. The residual plot for our house price example is shown. On the x-axis are the predictor values, x. The residuals are plotted on the y-axis. For reference, a red dashed horizontal line is placed at the mean residual value of 0. If our assumptions are okay, what we expect to see in the plot are points that are scattered around the mean line at 0 as we look from left to right, with no discernible pattern. That is what we see in this plot, for example. All the residuals are randomly scattered around the red line as we move from left to right. The residual plot is used to check the second part of our assumptions about the epsilon, that they have a mean of 0 and a standard deviation sigma. That is the same across all of our possible predictor x values. To explore residual plots further, let's look at a couple examples where the residual plot indicates a problem. Here's an example of a residual plot that does suggest a problem with the assumptions. The problem indicated by this plot is with the assumption that the mean of the distribution is 0 across all possible values of x. As we look from left to right, we see that the mean of the residuals seems to have a clear pattern from being negative on the left, then becoming positive in the middle, and returning to negative again on the right. That is, there's an indication that the mean of the residuals is changing as the predictor changes values, and in a systematic fashion. This is a violation of the assumption that the mean of epsilon stays fixed at 0 across all possible values of x, that is, as we scan from left to right. Here's a final example. Again, this is a residual plot that suggests a possible problem with our assumptions. The possible difficulty in this situation is with the assumption that the distribution has a fixed standard deviation across all the values of x. This is a residual plot suggesting a clear systematic pattern in which the standard deviation of the residuals increases as the predictor increases as we scan from left to right. This is a violation of the assumption that the standard deviation should be constant across all values of the predictor. This pattern where the standard deviation clearly and systematically changes with the predictor is called heteroscedasticity. This is in contrast to our assumption of an equal standard deviation moving from left to right, which is called homoscedasticity. Again, this is a type of residual plot suggesting a violation of an assumption about the error term epsilon. In discussing assumption violations, it's useful to make one additional point. One of the good things about plots like this is that not only do they help us detect violations of assumptions, but also they provide guidance as to steps we can take to correct such violations. When we see a violation of the assumptions regarding epsilon, there usually is something we can do about it. Recall that in specifying our regression model, step 1 of the regression procedure, we mentioned that the regression procedure is very general. The terms in the model can capture a variety of different kinds of relationships between y and the predictors, besides the linear relationships that are most common. In particular, if we observe a problem with the assumptions regarding epsilon, we can often add a term or apply a function to a predictor that allows us to correct the violation. We'll look at this idea a little bit later in the course. We will only touch on the topic in this course, though. Just be aware that when an assumption about epsilon is violated, there's probably one or more things that can be done to correct the situation that we might explore as needed. We continue our discussion of regression in this module with the discussion of using the model for understanding the relationship between the response variable and the predictor. Here, primarily focusing on doing this for the simple linear regression situation. Now that we have our model and the assumptions for doing inference with the model check out, we are ready to move to the next stage, listed as number 5 on the slide. The skipped number 4 only applies to the multiple regression situation that we will see in a later module. At this point, we have a model that employs a pair of beta constants that describe the relationship in the process between the response variable y and the predictor variable x. We have a fit of the model that has estimates, beta hat, that describe the relationship in the sample. Now we want to connect the sample and the process based on the assumptions we made. One use of the model that involves inference is description, specifically description of how the predictor x relates to the response variable y. Recall this regression model, shown for the simple linear regression situation with one predictor x. This is the hypothesized model of the process, in which beta naught represents the mean value of y when x equals 0. Beta 1 in the model represents the mean change in the value of y for every 1 unit increase in x for the process. Below that is the fit of this hypothesized linear relationship to the data. The fitted model captures our estimate of the linear relationship between y and x in the real world. One of the reasons we do modeling is to understand and describe how different components of the environment relate to each other. For example, how actions we take relate to the outcomes that we observe. The fitted model provides that description. It's our best estimate of what the relationship between y and x looks like. However, as always, we recognize that there is uncertainty in this estimate due to sampling error. Managing this uncertainty directly, we apply the inferential tools that we have developed in earlier modules. We make inferences from the beta hat that are known to the beta parameters that are unknown, but are what we care about. Ultimately, we want to know about the relationship in the real world, not the relationship in the sample. To do inferences about the 2 beta parameters in our model, as indicated, the appropriate statistic for inference about each of the beta I is its corresponding beta I hat. In each case, the beta I hat is our best point estimate of its beta I. We also have already seen the assumptions for regression, repeated on this slide. We also have seen how these assumptions can be checked. On the basis of the assumptions, we can identify the sampling distributions for our statistics, beta naught hat and beta 1 hat. In both cases, the sampling distribution has the form of the t-distribution with n-2 degrees of freedom for the simple linear regression. As we noted earlier, these are the degrees of freedom for the calculation of S sub epsilon hat, the standard error of the residuals, epsilon hat. The epsilon hat are the best estimates of the error terms epsilon in our process model. Having the sampling distribution, we are now able to do inferences about the beta I. We address the 2 main forms of inference, confidence interval estimation and hypothesis testing. For a simple linear regression model, we start with the hypothesis test on this slide that focuses on beta 1. This is the coefficient that is central to specifying any relationship between the 2 variables. Our null hypothesis H0 is that there is no relationship between y and the predictor x. As seen in an earlier module, no relationship corresponds to having a value of beta 1 equals 0. A value of beta 1 equals 0 indicates that the predictor can be removed from the model with no loss in explaining why. In contrast, the alternative hypothesis is that there is a relationship between y and x. HA corresponds with a value of beta 1 not equal to 0. The statistic of interest, beta 1 hat, after conversion to its appropriate z-score, has a t-distribution. We calculate the z-score of the beta 1 hat value under the assumption that h0 is true, since this is an hypothesis test. The t-observed value is calculated as shown. It is the best point estimate of beta 1, namely beta 1 hat, minus the value under the null hypothesis, which is 0, then divided by the standard error. The appropriate standard error is the standard deviation of the sampling distribution of beta 1 hat, our best point estimate of beta 1. The calculation of the standard error, S sub beta 1 hat, is not detailed here. Its formula is readily available if you're interested. For our part, we will get all these values from R or comparable statistical software. We would note two things about the values of the S sub beta hat. First, the values of the S sub beta hat differ for the different statistics, beta naught hat, beta 1 hat, and in the general case, for all the beta I hat. Second, the values of S sub beta hat depend on the standard error of the residuals that we saw earlier, the S sub epsilon hat. This latter observation gives another indication of the importance that the error term epsilon has for our regression model. The error term epsilon is an essential part of our hypothesized model. Completing the testing, we can use the t-observed value and the t-distribution to find our p-value, which is the area above t-observed and the corresponding area in the opposite tail, since this is a two-tailed test. The p-value is then interpreted in the usual way as the probability of getting a sample result as extreme as beta 1 hat in either direction, if in fact there is no linear relationship between x and y. In addition to testing, we also can be interested in estimating the magnitude of the relationship between y and the predictor x. We can do that in the form of a confidence interval, the formula for which is shown here, and that has a familiar form. The 1 minus alpha times 100% confidence interval for the parameter beta 1 starts with the best point estimate of beta 1, namely beta 1 hat. Then we have plus or minus the test statistic, which depends upon the form of the sampling distribution for beta 1 hat, and our acceptable level of error alpha. If the assumptions behind regression hold, then the sampling distribution has the form of the t-distribution with n minus 2 degrees of freedom for the simple linear regression. Finally, the test statistic is multiplied by the standard error of the sampling distribution of beta 1 hat. Again, the calculation of S sub beta 1 hat is not detailed here, but realize that it depends on the standard error of the residuals, S sub epsilon hat. As you can see, the test and estimate on this slide are both presented for the parameter beta 1 in the simple linear regression model. But there is another beta parameter in our model. What about beta naught? The parameter beta naught is the intercept value, and it warrants special attention. It is different than the beta values in the model like beta 1 in that it has no predictor attached to it. What about beta naught? As shown, we can do inferences about beta naught. The beta 1 hat terms in the formulas here just get replaced by beta naught hat. We can test whether beta naught equals 0 and we can calculate a 1 minus alpha times 100% confidence interval for beta naught as shown. Indeed, the information for doing inference for beta naught is readily available in the standard output that we get from R for regression. Compared to S sub beta 1 hat, the S sub beta naught hat is a different value for a different sampling distribution. Now for the sampling distribution of beta naught hat. But it also depends on the standard error of the residuals, S sub epsilon hat. However, we need to be careful in using this output and be clear about interpreting the information correctly. In fact, in most decision situations, the value of beta naught has no real-world meaning. However, occasionally it does. Recall what beta naught is and is not. It does not represent the relationship between y and a predictor. So the test that beta naught equals 0 or beta naught does not equal 0 is not a test of any relationship. Let's consider what beta naught represents for the general case of multiple regression, in which we have multiple x terms in the model. In the general multiple regression, beta naught represents the value of the mean of y when all the x values in the model equal 0. In order for beta naught to have real-world meaning, two things must be true. First, it has to make logical sense for all the predictors in the model to take the value of 0 at the same time. If it is not logical for any one of the x to have the value 0, or for the x values to all be 0 at once, then it does not make sense to talk about a value of y when all the xi equals 0. Therefore, beta naught has no interpretation in such a problem context. For example, suppose we are in a corporate setting and one of the predictors x in our model is the age of the employee. It would not make sense for x equals 0. No company is hiring newborns. For a model with age as a predictor, the beta naught for the model would have no real-world interpretation in this setting. In addition to x equals 0 making logical sense for all the predictors, a second condition also must hold in order for beta naught to be interpretable for a fit of the regression model that we have. This second condition relates to a consideration that is a more general caution in the use of models in general. In using models, we want to be careful of drawing conclusions that are outside the range of the sample information that we have. Within the range of our sample data, the data provide information about what is happening for the process. However, if we are using the fitted model outside of the range of our sample data, we do not have any information about what is happening outside the range of our sample data. This becomes increasingly problematic as we get further outside that range of our data. Let's apply this idea to our ability to interpret beta naught. This caution means that beta naught will not be interpretable in the problem context if x equals 0 is well outside the range of our sample data for any of the predictors in the model. For example, as is in the case of the figure, the beta naught value at the red question mark in the figure is well outside the range of the data. In such a situation, any test or estimate of beta naught is also meaningless. In practice, it usually is true that one or both of these conditions is not met, leaving beta naught to have no interpretation in context. Occasionally, it is both logical and within the sample range that xi equals 0 is possible for all the predictors in the model, but usually this is not the case. We always need to be careful about interpreting beta naught and be sure that it is in fact meaningful for the decision situation. Let's now look at sample R code and connect it with our discussion. We conduct a simple linear regression with house price as the response variable, measured in thousands of dollars, and size of the house as the predictor, measured in hundreds of square feet. Both are interval level variables. The R function Lm constructs the linear model for these two variables and stores the results of the model fitting in the data frame fit. We use the summary function to get information concerning the beta hat that are the estimates of the beta values in the model. In this part of the output, the row labeled intercept provides information regarding beta naught hat. The row labeled size identifies the predictor variable x and provides information about beta 1 hat. The column labeled estimate shows the beta hat values, calculated from the sample. Beta naught hat equals 48.02 and beta 1 hat equals 5.7. Since a house size of 0 is not logically possible, beta naught and beta naught hat are not interpretable in the problem context. The intercept row can therefore be set aside. The value of beta 1 hat is interpretable. Recall that house price is in thousands of dollars and size is in hundreds of square feet. Each additional 100 square feet of house size relates to an average price increase of $5,700 in our sample. The next column is labeled STD error. This column contains the standard error of the sampling distributions for the beta hat statistics. The standard error, that is the standard deviation of the sampling distribution for beta naught hat, S sub beta naught hat, equals 14.41. The standard error of the sampling distribution for beta 1 hat, S sub beta 1 hat, equals 0.75. Recall, these values are different, being for different distributions, but both depend on the value of S sub epsilon hat. The next column is labeled t-value. These t-values are as discussed on an earlier slide. The t-value is the observed t-statistic for the hypothesis test, where h0 is that the beta equals 0 versus the ha that the beta does not equal 0. As described earlier, the t-statistic equals the estimate beta hat value minus 0, the hypothesized value under the null hypothesis, divided by the standard error of the beta hat. In this example, the t-statistic equals 5.7 minus 0 divided by 0.75, which equals 7.64. Note that the 0 in this calculation comes from h0 and ha. For hypothesis testing, we assume the value under h0 until and unless we have evidence to the contrary. And for the output produced by R, it is presumed that we are doing the two-tailed test with h0 beta 1 equals 0. Since beta 1 is the mean of the sampling distribution of beta hat 1, this is the appropriate calculation for this hypothesis test. If the hypotheses were different, we could still find the observed t-statistic using the beta hat 1 and the S sub beta hat 1 provided in the output and highlighted in red. This t-statistic, assuming h0 is true in the regression assumptions, has a t-distribution with n minus 2 degrees of freedom. We can use the t-statistic of 7.64 calculated from the sample data and this sampling distribution to find the p-value for the test. By default, R does the two-tailed hypothesis test with the HA as specified in the title of the slide. Our two-tailed p-value is the area above 7.64 plus the area below minus 7.64 for the t-distribution with n minus 2 degrees of freedom, like the gray shaded region in the figure. The p-value equals 6.05 times 10 to the minus fifth and is interpreted as usual. It is the probability of getting a t-value at least as extreme as the value that we observed in our sample, if in fact beta 1 equals 0. That is, it is the probability of getting a sample result as extreme as the one we obtained if there is no linear relationship between house price and size. The p-value is very small. It's very unlikely that we would have gotten a sample result this extreme if there were no relationship between house price and size. We would conclude a relationship. Finally, we finish with an example of finding the 1 minus alpha times 100% confidence interval for beta 1. The interval starts with the best point estimate of beta 1. This is beta hat 1 equals 5.7. We also will need the standard error of the sampling distribution of beta hat 1. This is S sub beta 1 hat equals 0.75. Finally, we need the t-statistic for our acceptable level of error alpha. Suppose alpha equals 0.20. We want an 80% confidence interval for beta 1. As shown, we can use the QT function to obtain the value associated with alpha equals 0.20. Confidence intervals are two-tailed, so we want alpha over 2 equals 0.10 outside of each side of the confidence interval. The needed t-statistic is t.10 value with 8 degrees of freedom. Our n here is 10. This equals minus 1.4. We can then put these three pieces together manually to calculate the 80% confidence interval for beta 1, using the formula seen earlier in this module. The three indicated values are combined as shown to arrive at the 80% confidence interval for beta 1, equals 4.66 to 6.74. More simply, we can use the conf_int function within R. The syntax is shown here. Same intervals obtained as shown in the bottom row in blue. For now, this completes our discussion of using the model for descriptive purposes using the fitted coefficients, particularly beta 1 hat as an estimate that describes the relationship between the predictor x and the response variable y. In this module, we focused on the description of the x-y relationship within simple linear regression. We'll have more to say about description within multiple regression in a later module when we introduce multiple predictors, describing multiple relationships. We now continue with the final step in the basic procedure for doing regression, covering two other common uses of the model that we've created, both connected to the response variable y. In the first part of step 5, we focused on the linear regression model with a single predictor. We used the fitted model as our best description of what the hypothesized relationship between the response variable y and the predictor x looks like in the process. We can now also use the model to say something about the target variable of interest, that is, the response variable y. There are two common uses of the model with respect to the response variable y. One of these is to use the model for estimating the mean of y in the presence of the relationships with the predictors. Earlier, we developed a procedure for estimating a process mean mu. This was done solely using sample information about y. In that case, y bar is our best estimate of the process mean of y, and we can construct a confidence interval estimate for the mean of y centered at y bar. Now, we not only have the values of y in our sample, but also we have some predictors that we believe are related to y. Using this new information and the model that captures the relationships, we can better estimate the process mean of y. That corresponds with the estimation use of a model. We can use the model to come up with a better estimate of the mean of y by capitalizing on the relationships between y and the predictors in the model. The third major use of a regression model is prediction. Sometimes we're interested not just in estimating the mean of y over a comparable set of observations, but also we're interested in predicting a particular value or set of values of y for a specific situation. We will begin by discussing the estimation use, estimating the process mean of y for a given set of predictor values. We turn to the estimation task. As before, we will demonstrate estimation while focusing on the simple linear regression model so that we can visualize the inference. Note, however, that everything here extends in a straightforward manner to the multiple regression situation. For simple linear regression, we're interested in estimating the mean of y for a given predictor value x. Having a model, we can capitalize on the relationship between y and the predictor x to come up with a better estimate for mu of y than we could before. As we saw in an earlier module, the y hat values for our fitted model correspond to a line of estimated sample means. The points on the line represent our estimates of the sample mean values for y given different values of x. Using our model, our best point estimate of the mean of y, now that we know the predictor x, will be y hat, calculated from the model. We use our model to calculate the y hat that is our best point estimate of the mean of y for the portfolio of all members of the process who share the value of x. But we're not just interested in the best point estimate, we're also interested in how good that point estimate is. An interval estimate serves this purpose. Shown here is the formula for the interval estimate of the process mean of y, mu of y, for a given portfolio of individuals defined by the desired value of x. The formula follows the general form for confidence intervals that we've seen before. The interval is our best point estimate, namely the y hat corresponding to the x value of interest, plus or minus the test statistic times the standard error of the sampling distribution. The sampling distribution under the assumptions made, and for simple linear regression, is the t-distribution with n minus 2 degrees of freedom. These are the degrees of freedom for the standard error of the residuals, the s sub epsilon hat. The formula for the standard error of y hat, s sub y hat, given x, is not detailed here. For the simple linear regression, it is available in most any introductory statistics text if interested. Of note is that the calculation of this standard error involves using the standard error of the residuals, the s sub epsilon hat. Thus, the degrees of freedom for our test statistic t is connected to the calculation of s sub y hat given x, which in turn is connected to the degrees of freedom for calculating the s sub epsilon hat. For the simple linear regression, this degrees of freedom is n minus 2, as we have seen. We use the alpha over 2 value of the t statistic in calculating the 1 minus alpha times 100% confidence interval. And we multiply by the standard error of the sampling distribution for our best point estimate, which is s sub y hat given x for the given value of x. Let's take a look at what the confidence intervals look like for the simple linear regression situation in order to get a visual sense of them. We start with our fitted regression line illustrated for the simple linear regression situation with a single predictor x and a response variable y. The sample mean x bar is displayed. The point on the fitted line is x bar y bar, since the fitted line always passes through this point. Our fitted line is y hat equals beta naught hat plus beta 1 hat times x. Also shown on the graph is a value of a predictor labeled x1. For every value of x, like x1, the line gives us a value y hat. The y hat is the best estimate of mu of y for that x. The best point estimate of mu of y for x1 is the point on the fitted line y hat 1 equals beta naught hat plus beta 1 hat times x1. Using the formula from the previous slide, we can create a confidence interval for the process mean of y, given x1, now shown in the figure by the blue bracket. It is centered at y hat 1, which is the value of y hat when x equals x1. It extends above and below y hat 1 by an amount t times s sub y hat 1. The standard error, s sub y hat 1, is the standard error of the sampling distribution of y hat when x equals x1. The bracket represents the hedge for the sampling error associated with this inference. As another example, this is the confidence interval for the process mean of y given a different value of x, x2, shown by the red bracket. It is centered at y hat 2, which is the value of y hat when x equals x2. It extends above and below y hat 2 by an amount t times s sub y hat 2. Standard error, s sub y hat 2, is the standard error of the sampling distribution of y hat when x equals x2. As a final example, this is the confidence interval for the process mean of y given x bar, shown by the green bracket. It is centered at y bar and extends above and below y bar by an amount t times s sub y hat given x bar. Here, all three of the intervals are shown for the three different values of x, x1, x2, and x bar. Note that the t-statistic and the confidence level, 1 minus alpha, are the same for all three intervals. The only difference is the value x being looked at, which impacts the standard error for the interval, s sub y hat given x. Besides these three, we can find a similar interval for any value of x in this range. The intervals we would get for any value of x are indicated by the two purple curves in the figure. The purple curves show what the confidence intervals look like as x varies. The curves show one feature of the intervals for estimating the process mean mu of y at different values of x, and this feature is true in general. Namely, the confidence intervals are narrowest when estimating mu of y at x bar, and the intervals get wider as we estimate mu of y further away from x bar. Thus, the interval estimate of the process mean of y is most precise, narrowest, at the sample mean x bar. When we're trying to estimate the process mean of y further from x bar, we have less precision. And this should make some sense. X bar is the central tendency of the x values in our sample. When we are using the sample information to estimate around x bar, we have a lot of information about what's happening, both above and below x bar in our sample. We have a relatively good sense of what the relationship between x and y looks like around this central value x bar. Contrast this to a situation where we're at the far right of the values of x in our sample, for example at x1. At x1, we have a lot of information about what's going on below the x1 value, but we have very little information about what's going on above the x1 value. Less information means more uncertainty, less precision, and wider intervals. Since we have increasingly less information about the relationship between x and y as we move away from x bar, we expect increasingly wider intervals. And this is in fact what we see generally for any regression. Besides estimation of the mean of y for a given set of predictor values, the other common use of the model with respect to the response variable y is for prediction. In prediction, we are not estimating the mean of y for all situations that have the portfolio of a predictor value x. We are interested in predicting a specific value of y associated with a specific predictor value x. For example, an estimation task might involve estimating the mean household price for all houses that have a house size of 2,000 square feet. A prediction task might involve predicting the household price for a single particular house of size 2,000 square feet. Now, we could manage the uncertainty involved in prediction in the same way as we did for estimation, namely by constructing a prediction interval. And there are procedures for doing this. However, prediction intervals are a rather imprecise way of handling the use of models for prediction, so they're not often used in situations where we are building a model to use for prediction. Instead, briefly introduce the procedure that is typically used when we are building a prediction model. We won't demonstrate or put this procedure in practice for this class, but you will certainly use the procedure with other courses within the program. Let's just touch on it here to be aware of it. The basic procedure is one of predictive validation. It's a way of testing a model for predictive use and of getting an idea of how good the model is for that purpose. The general procedure involves the use of at least 2, ideally 3, data sets. The data sets might be obtained by partitioning a sample data set into 2 to 3 pieces prior to analysis. The resulting 3 data sets each serve a different purpose, as described here. One of the data sets is used as a training data set. When we're doing multiple regression and have multiple predictors available, we usually try more than one model, checking to see which model works best. We'll see more about this in a later module. For the predictive validation procedure, the training data set is used to fit the models. For regression, we use the training data set to derive the beta hat values for each of multiple possible models. The second data set is often called the validation data set. In this procedure, the validation data set is used to assess the performance of the model. We test the fitted models created with the training data set and see which of the models does best for the validation data set. We then use the performance on the validation data set to select our best model, based on whatever performance measure we deem appropriate. Why do we not assess the predictive performance using the training data? What's the need of a separate validation set? The reason that we separate the stage of fitting the model from the stage of evaluating the model's performance is primarily due to a phenomena in modeling called overfitting. Overfitting a model is the danger of capturing relationships that only exist in the sample data, but do not hold for the process more generally. We reduce this danger by separating model fitting from model evaluation. We fit each model with the training data set as one sample, but we make the decision about which model is best using a separate data set used as a separate sample from the same process, the validation data. Sometimes this is as far as the procedure is taken, but it is not unusual to apply a third data set following validation. After selecting the best model based on performance with the validation data set, we might want to get an idea of how the model will perform as a prediction model on a new set of observations, comparable to the future observations that we will use the model to predict. This is often called the testing data set. We take the model we're about to use as our prediction model and apply it to the testing data set as a separate sample of the process. This provides a prediction of what kind of performance we will expect when we use the model in a new situation that we are trying to predict. It provides an indication of the expected future performance of the model that is independent of the data samples that were used to build and select the model. Again, we won't be demonstrating the predictive validation procedure shown here in this class, but be aware of it, and you will see more about this in other courses within the program.